Hello, and thank you for attending today's seminar, Introducing an Upper Bound Constraint to the Inversion Process. This is part 2 in the series designed for VOXI pre-released program participants. My name is Brad Johnston, and I'll be your moderator today. I'd like to pass this over to Troy Wilson to do some introductions. Thanks.
Thanks, Brad. This is Troy Wilson. I'm the team lead for the VOXI Earth Modeling team. As always, we're delighted to have all of you signed up for the program. Look forward to working with you and hearing your feedback on our new inversion service. As part of the program, Geosoft is providing ongoing series of learning webinars focused on understanding how to use our VOXI Earth Modeling service. Today's seminar is the second in our series. It is focused on the use of constraints within the VOXI Earth Modeling service. We hope by the end of this seminar you'll have a better understanding of when and where constraints can be used to improve your results. Both Rob and Elizabeth will be taking you through some case studies that use inversion and constraints to resolve exploration problems. Brad, as he's introduced himself as a moderator, will help field questions to both Rob and Elizabeth. So without further ado, I'd like to pass on to Elizabeth, who will begin the seminar series.
All right. Today, I will start with a review of the unconstrained inversion that we walked you through last week. The reason for doing so is that usually when you run an inversion on a data set, you do it through a few trials. You start with a simple inversion and then you keep building on it. So instead of running through it again through the unconstrained, I thought I'll review the data to refresh your memory. And for those that haven't been with us, so that you know where we are going and what data we are using. This is the Reed-Mahaffey data that I have on the screen in the 3D viewer. The data set that you see is the MAG data as well as the terrain. And underneath, semi-transparent, we have the unconstrained voxel model. Now, last week we exported also the calculated model that I will turn on right now, turn on and off a couple of times, and you will see that the fit is pretty good. So we managed to fit the data. However, this is only one of the many models that can fit our data. What we are going to do now is to try to go closer to a model that is closer to the geology. And for that, we need certain information, a priori information. Before I move from here also, I thought I will show you the high susceptibility areas. The model that we produced, kind of because we didn't have any constraints, tends to push all the high susceptibility zones to the surface. With this data set, another data set and information that we have available to us is the calculated EM conductors. I want to make this smaller. So we do have, through some earlier project, the depth to the top of the conductor. We do have the DEM. So we can calculate a surface that represents the top of all the conductors. No conductors are above this depth. So let's stipulate, it may not be very true, but for the purpose of the exercise, let's stipulate that there is a direct association with a high susceptibility, between the high susceptibility units and their conductivity. And we will say that we would like to model and add a constraint whereas you have no high susceptibility values residing above this conductor layer. In other words, we don't want to have any high susceptibilities between the surface and this layer. All right, now we are going to move into VOXI with that in mind. Oh, by the way I produced this surface is through that database that I showed you. I simply gridded the depth channel. So I will go into VOXI. Let me actually minimize these background images. And I will impose an upper bound constraint. To the same data. I have from the previous exercise the polygon polygonal area that I will be modeling. I do remember that I had downloaded the DEM from Seeker right from within Oasis Montage. The 50-meter grid cell is good. I did already that exercise. I'm happy with that. And the data set that I used is the grid Mahaffey. Oops, I picked the wrong data set. Bear with me. There we go. It recognizes the X and Y channels. We tell it what the elevation channel is. It is a susceptibility model. I'll pick the observed and corrected MAG channel. The error margin for me is calculated to be 5% of the standard deviation of the data, which is good enough. The parameters of the IGRF field are calculated on the fly because my database happens to have the date of the survey. I don't want to remove any background from the data because it is residual data. And now I'll be ready for my inversion, except that the difference is this time I'm going to go and add an upper bound voxel. Now, there is a step that I missed. I showed you the surface below which I want to have my high susceptibility values. The step that I'm not going through right now, but I'll mention it, and it by itself is another area that we can cover elsewhere, is that I use that surface to generate a voxel for which the upper susceptibility above the conductor surface, I said I want to limit the susceptibilities to a small value, and I allowed it to be much bigger below. I will load that voxel that I produced . And let me turn some stuff off. It's a bit too crowded. There we go. So here is my voxel. I did voxel math, and I said, given the surface that lies right there, set everything above to some small value, 0.001, as the upper limit that my inversion will reach. And I have this low value up here and a much larger down below. Now, very quickly, just to say where I came up with those values, if I look at the model that I produced in the unconstrained inversion, and I run some statistics on it, I see that without any constraints, my susceptibilities lie between minus 0.003 and 0.08. Just looking at these values, I thought, okay, I'll set my upper bound for the top here to 0.001. That's small enough. But I'll make my lower bound, the limit, much higher than this, because I know as I push the data down, I need higher volumes or larger susceptibilities to produce the same response at the observation level. All right, now that we have this, let's just run the inversion. 29 tokens, just like when I ran the unconstrained inversion. I will start the inversion. We spoke about this last week a bit. What is happening right now is that we are uploading the data to the cloud. The cloud is Microsoft's Azure cloud, and it's actually a computing cloud. It is not a storage cloud. This data goes up to, for me, being here in Toronto, to a location in Chicago, where actually Microsoft has the size of 2 football fields of processors. These agents are sitting there. We have some that are turned on all the time, but we can expand the number of agents that are working depending on the need. So sometimes you may see on your screen that it says you may need 15 to 30 minutes to trigger new agents. That's because at that point all the agents are in use, we need new agents, and that's all the time it takes to fire up a machine and install the operating system, install our software, and be able to run your inversion. While this is running, if we look at the other options that we have, there is a large number actually of constraints that you can impose. Depending on what you know, what your geological structure is, if you have any contact information, you will use a certain number of these. You can use one, up to 3 or 4, but you won't use all of them at any one time. For example, the starting model, if you have some prior knowledge, if you modeled already your data, or if you have drill hole information, you may start with known voxel values so that you decrease the number of iterations and your inversion happens faster. Or if you do have any contact information, you can use a combination of a gradient reference model, which is very similar to setting up a startup model, as well as the weights in the 3 cardinal directions, the weights along those contact areas. But I'm not going to go into any detail on these various aspects because today we are covering only one of the constraints. After my presentation here and showing you the results and comparing the results with the unconstrained, Rob Ellis will show you a similar exercise with a different data set and a different upper bound system, upper bound voxel. So I hope that that altogether will give you a good notion of how to use the upper bound constraint. Of course, as I mentioned the first time, I can go now into the journal and add some information about what is different between this inversion and the previous one. I think in the meantime, I am going to turn off, now that we saw the upper bound, I'll turn it off so that, okay, I do get now my results. Shortly I'll be able to display it. There we go. You will notice now that the susceptibility, the higher susceptibilities, which are shown with the warm colors, are pushed below the surface that I had imposed. All right. This is good, but I want to compare this one with my earlier unconstrained inversion. So I'm going to do 2 things. First, I'm going to export this voxel as, export it out of VOXI as a voxel model. There we go. And bring it into my 3D view. The other thing that I can do is export the calculated forward model or forward magnetic response into a database. And I can do that by going here, predicted response, and export it. There we go. And now I have it in a database. So I can use Oasis Montage to do different things. For example, grid, my calculated response. I'll look at the observed and the calculated response and see how closely they match. I showed on the 3D view, actually what I showed you earlier is the same comparison of the 2 fields, but in a 3D view. I can take now these out of the way. And let's come back in here. I can now import the voxel as well as calculate the isosurfaces for my new model. I already loaded those in here. So here is my constrained voxel. And I calculated the isosurface by going here, the isosurface at the exact same value, the 0.015 that I have loaded already. I will show you that, and let's remove what clubbers. There we go. And what you see right now is that in the pink high susceptibility isosurfaces, you see the unconstrained inversion, while the red ones show us the constrained inversion, where we pushed all the high susceptibility zones below that conductor surface. And we see that the volumes are larger, they're sitting below the surface, and they produce a very an acceptable, very close to the observed magnetic response. I'll just turn on and off the second one. There we go. This is the outcome of our unconstrained inversion. All right, this concludes my presentation. I will now pass it on to Rob, who will show you a upper bound constraint inversion with different data. Thank you.
Thank you, Elizabeth. I think we can all see that that's an excellent example of how to use an upper bound constraint to force an inversion result to produce a model which is much more geologically reasonable than a simple unconstrained inversion. I'm going to continue the focus on using an upper bound constraint. I'm going to firstly begin with a few PowerPoint slides to explain what I'm going to do and the problem I'm dealing with, and then I'll go through and do a demonstration of using VOXI as Elizabeth has done, and then we'll finally conclude with comparison, again like Elizabeth, of the unconstrained and constrained inversions. So let me begin the PowerPoint presentation. I'll first start off with a description of the exploration problem. In this case, it's VMS style deposit. It's got some sediment cover, and there's possibly some fault constraint on the deposit. I'll go through and I'll show you how you can use upper bound constraints to implement this fault control and this sediment constraint. I'll then go through and actually describe briefly how you can build the constraint model using voxel math. Elizabeth touched on that, but I'll take it a little bit further. We'll then run the inversion, and then we'll compare the results, and again we'll see that we're able to produce a model which is much more geologically reasonable. But as I said, first I'll just show you as a series of PowerPoint slides what we'll be doing in a moment. The problem I'm working on in this case, it's a simulation of the San Nicolas property in central Mexico. We know, as I've said, that this is a VMS-style deposit. We've got some sediment cover, approximately 200 meters thick, and we expect the deposit to be constrained by a sort of a southwest trending fault that runs through the property. So what I want to do now is take gravity data that's been simulated over that structure and then invert it using constraints to try and produce a more useful geologic model. Okay, so the first thing we do is bring our information together in our 3D view so we can see what's happening here. I know that for these styles of deposits, the ore density is maybe between 4 and 5 grams per centimeter cubed, and the host rock in this area is between 2 and maybe 3 grams per centimeter cubed. So this is a situation where the potential ore density is much greater than the surrounding host rock. We've got sediment cover about 200 meters, and I'm arguing geologically that any ore zone should be excluded from those sediments. What I'm showing you here on the right-hand side of this image, this slide, is on top this bluish hue represents the surface of the property, and I've got a horizontal yellow gold layer here shown in the model. This represents the base of the sediments, and in this case that's been determined by some other geophysical methods and potentially some drilling. This would be similar to Elizabeth's situation where other geophysics is used to determine some constraint on the potential field inversion. Next, in this, I can see that there's a mapping as indicated in some drilling that there's a southwest trending fault. This model is slightly rotated, but in any case we have this green fault running through the property, and we expect any potential ore zone to be on the east side of that fault. So we've got two constraints. One, we've got a vertical fault constraining the deposit to be on one side. The deposit to be on one side of that fault, and it must be below this upper surface. So how can we implement that into our voxel inversion? Well, one of the fundamental things to understand about VOXI and VOXI constraints is that they must all be entered as voxel models. So the first thing we need to do is take our geologic information, which we have in terms of these faults and the unconformity, and turn that into a voxel model. So this is what I'm showing you here in this slide. I'll describe this a little more when we go through the actual demonstration. But here are my constraints shown, the fault in green, and on the left-hand side of your screen from that fault, I've assigned or created a voxel model with a low value of physical property. So let's just say, for simplicity, that this blue zone represents a value of 1 in a voxel model. Sorry, a value of 0 in a voxel model, a low value. And then above this surface, the sediments in this model, I've also assigned that a value of 0 in this voxel model. And the remaining zone shown here in this yellowy color, I've assigned a value which is significantly larger than that, maybe say 5. It doesn't really matter, but as long as it's sufficiently large to allow any potential ore zone to manifest itself. So in essence, I've converted my geometric constraints into a voxel model. So this would form an upper bound, potentially an upper bound model to go into my inversion, with the blue zone being 0 and the yellowish zone being 5. This will, if I implement that as an upper bound, force any density that's recovered by this gravity inversion into this yellow zone. So let's see how this works. Okay, before I do that, I of course will show you the inputs to VOXI in this case. Again, we always have our survey boundary shown as this black polygon drawn on the gravity data itself. And this is this property here is about 3 kilometers by 3 kilometers. I've also got the DEM in that area. This is the other, or the third component of the input to VOXI. So I have my necessary inputs for a standard unconstrained voxel inversion, and what I also need is the basic inputs for a constrained inversion, the survey boundary, the terrain, and the data. And you can see that there's a gravity anomaly right in the center of this area. Now, if I run a simple unconstrained inversion, I will end up getting a model. I do end up getting a model that looks like this. Effectively, it's a typical, let's say, blob type solution that comes from a standard unconstrained gravity inversion. It puts a target down at about 200 meters. So this is a very good starting point for an unconstrained inversion. It's shown that everything is working normally, but if I look at that unconstrained inversion and I put it in together with the constraints that I have, you can see that the model itself actually extends well into this sediments, and it's not really strictly bounded by this fault. So this is my unconstrained inversion results. This is my geologic information. We can see that the two aren't really very consistent. So obviously, if we're working in our exploration team, it's going to be a much better accepted result if we're able to make the inversion consistent with the geology. So that is our real goal for doing these constrained inversions. Okay, so what are the steps required to go through this process and to actually create the upper bound model? Well, as I've described before, and just a few moments ago, my aim is to construct a voxel model which has 0 where this is blue, and I'm going to say 5 where this area is yellowy coloured. And the way I do that is quite straightforward and is a simple use of voxel and channel math. I'm going to show you a process or describe a process here, and we'll talk about it a little more in the demonstration. The first thing to do is run your unconstrained inversion. So we've already done that. We've got our unconstrained result. We're happy with everything. And I would emphasize this very strongly before you go into any constrained inversion. Make sure you run an unconstrained inversion and everything is working reasonably. So when I've run my unconstrained inversion, I've obviously got a mesh that has been used in that unconstrained inversion. The first thing I do is export that mesh to generate the general voxel structure that I need. So the mesh just is exported, and in essence it has no voxel values in it. Now I need to populate that mesh with the appropriate values for the upper bound constraint. So one way to do this, and as in most things, there are many ways to approach this problem, but the one that I'll show in this case is firstly I take the mesh voxel and I export it to a GDB. In that process I will end up with my GDB shown here with X, Y and Z locations which describe the voxel locations, and then I'm able to populate that voxel with values which allow me to construct via channel math an upper bound constraint. So let me explain how I would do that, and Elizabeth described this briefly previously. I have my voxel now, and before I populate these values in it, I've just exported it from the mesh. It just has X, Y, Z in it. Now, if I have my grid, which represents the base of the sediments, shown here in this yellow gold color, I can go and execute a sample grid to database. And what that will do is it will take this gridded surface and it will sample it into the database. And I've done that process and called it sediments. So having the grid here, sampling it to the database, I can see that my sediment layer in this part of the model, which I've just shown here, these XY locations, is actually down at 101.3 meters. The surface at that particular point is, yes, I'm sorry, so this is the value of this surface across the model here. Now I can do some channel math on that process, on those channels, and then I can use that to generate an upper bound. So for simplicity, what I can say is if the Z value of a voxel element, shown here, is less than the sediments, then set this value to be large, and set the value to be large, that's right, it's in this part of the model, and if the Z value is greater than the sediments, set the upper bound to be small. So this will generate zeros in the upper bound model everywhere above this surface. I can do the same thing with the southwest trending fault through the model. I can say everything to the where x is less than the southwest trending fault should be 0, and everywhere where it's greater I'm going to set it to 5. And I can use my channel math expression builder to construct such an expression by saying that the output channel is constructed from Z being less than the sedimentary layer and X being greater than the southwest trending fault. If that condition is true, set the voxel value to 5, and if that is not the case, set it to 0, and this will generate this particular voxel model for you. So this is how you build a constraint model, or at least it's one method of building a constraint model. Okay, now so I've done that process. I've generated a upper bound voxel. I've shown it here being imported into VOXI through the upper bound constraint, just like Elizabeth did. And I've chosen my voxel model. I've said OK. And then I've run the inversion. Now, what I'm showing you here in this slide is a comparison between the unconstrained inversion result, which we talked about a few moments ago, and now our new constrained inversion result here. What you can see from this constrained inversion result is that now the density is constrained to be in the region below the sediments. So this is a much more geologically meaningful result, and as a geophysicist, when you present results like this which actually obey the geology, there's a very, very positive response from the geologists and other members of your exploration team, because you're now presenting something which relates to the concepts that they understand in terms of how the deposit may be placed in this property. So what we've gone is from this unconstrained result, which doesn't obey the geology but is geophysically reasonable, to one that is now geophysically reasonable and obeys the geology. So that's the overall process. Now what I want to do is just show you how that works in VOXI. Elizabeth has already done this, so you've seen the operation. I will repeat that and try and emphasize some extra points so that you get a better feeling for how this process works. So let me transfer now over to VOXI. Here's my OASIS montage window. The first thing I would do, as I've explained before, is to, and as Elizabeth explained, and we also went through in an earlier webinar, is to start a new voxel inversion. We will do that from a polygon. What I'm showing you here is this dialog. I've pre-populated this just in the interests of time. We've entered our polygon file, we've entered our digital elevation model, we've chosen a model resolution. Now we say OK to that. VOXI goes off, constructs our model space for us, and we want to add some data. In this case, I'll just go straight ahead and add data. It starts up the data wizard, and I'll need to select my gravity data shown here. It's the same data that was gridded up and that I showed you in the PowerPoint presentation. Chosen my X and Y channels. My sensor elevation in this case is ZOBS. I'm going to optimize my data sampling. I'm going to say yes to that. The model type is density and it is gravity data. I need to select my gravity channel, and an error has been assigned to that data based on the standard deviation in the data. In this case, yes, I will remove a background trend from the data, and I will say finish to that. My VOXI session is now populated. I will show you the data. The data locations shown here, color-coded by value. Remember, this is the high value of the anomaly in the center of the project area. My mesh has been designed, and I'm good to run that inversion. So my next step would be to simply run the inversion, that is to run an unconstrained inversion and generate my unconstrained result. I will skip that process because we're in the interests of time. I think it's straightforward now. You would press the run button and the results will be generated. What I'm going to do is go through and show you how to work with this upper bound constraint, since that's the focus of this presentation. So as I said in the PowerPoint presentation, the first thing to do, since I have my constrained information, is to look at it in Oasis Montage, and here's my my constraint information. You can see here, I hope, the base of the sediments shown in this yellowy gold color, and my fault running through the model. And if I orient that in the normal direction, you can see that it is a southwest trending fault. And what I'm going to do is set up an upper bound constraint so that all the or the majority of the density that's recovered will form below this surface and to the right of this fault. So let me go back to my voxel session. The first thing I would do is go up here, and as I said, I need to take that geometric information, if you like, and turn it into a voxel model. So I need my raw material, if you like, to start this process, and the way I get that is to export the mesh file. So this could be my my mesh. I will save that. And what we see here is the mesh file. It's been exported. This is the raw block of material, if you like, that I will use to construct my upper bound constraint from. The process that I described to you would be to close this model and then go to my 3D view, and I will do a voxel conversion from a voxel to a GDB. So I'll just call that mesh as well, so I know the two are related. All right, so basically here I've shown you now, I've taken the voxel model, I've converted it into a X, Y, Z location for each voxel element, and every element from the mesh has a value of 1 in it. I'm not too interested in this. This is just the base model from which I would now go through and work with my constraints. So now what I would do is I can go to my grid utilities, and I can sample a grid. I need to choose a grid to sample, so I'm going to call this SED for sediments, and I'll choose a grid representation of the base of the sediments. Say OK to that, and then I will sample that into this database. Okay, so now I have my X, Y, Z locations, and I have my base of sediments at every X, Y location. Now, as you can see, it's fairly straightforward matter to run some channel math on that particular process. So if I go to channel tools, and now I go down to my channel math, I can create a simple expression. If the Z value in here is less than sediments, set the value of the channel, which I'll call upper, to 5, and if it's if it does not satisfy that case, if Z is greater than the sediments, we'll set it to 0, and I will just say OK to that. Now I have my X, Y, Z locations in my upper bound. It's straightforward now to go to 3D Tools, go to Voxel Conversions, convert my GDB back to a voxel. We'll call that upper. It's going into the right place. I'll say OK to that. And here I now have this upper bound constraint voxel. I've shown you that everywhere above this sediment surface, everywhere above the sediment surface, the value of the voxel is 0, and everywhere below it is 5. So I've created an upper bound constraint representing the sediments. Now, the model that I'm using also has a southwest trending fault through it. I would go through the same process. I won't repeat that in the interest of time, but I would go through the same process to construct that or add that constraint to this model and generate my full upper bound constraint. So now I will close these down. I don't need to save that. And here I am. I'm back in this particular situation. And now I would go down here to my constraints and choose my upper bound constraint. Just as Elizabeth had done, you can currently see the tooltip says it's not used. So I need to turn that on. Modify. Choose voxel. Choose my voxel file. And were I to choose the one I just created called upper, I could say open to that, OK. And now you can see that's been brought into my voxel workspace, my VOXI workspace. I can turn it on, turn it off, and I'm ready now to run my voxel inversion. So it's a simple matter of hitting the run button, and this inversion will run with the upper bound constraint. Now I'm running a little out of time here, so I'm not going to make you watch while I run this. I'm just going to close this down and show you the results where I've made a composite of the results of running these inversions in here. What I'd shown you earlier was the unconstrained results, so if I turn that on, you can see that here is the unconstrained result, penetrating up through the sediments, not a very realistic geologic solution. If I now turn it off and I turn on my constrained inversion result, you can already see now that the result is satisfying my geologic constraints, and you can actually see that the density model itself, which I'm showing here, the high density, actually comes up and meets this surface here but does not penetrate through it. So we've seen here that we can go from the unconstrained result, which is geologically unreasonable, to a constrained inversion result using this upper bound constraint in VOXI. And all this we can do in a relatively short span of time. So this is a very efficient and effective way to make your inversions far more consistent with any known geology. And as I said earlier, one, as a geophysicist, cannot underestimate the value of, it's extremely important in conveying your geophysical results to the rest of the exploration team if they in fact respect the geology and constraints that the rest of the exploration team, particularly geologists, are expecting. So I think that concludes my presentation here, and I will now turn this back over to Brad question and answers. So thank you all for listening to that. You can find more information about this building of constraints and using VOXI on our website. Okay, thank you.
Thank you, Rob and Elizabeth, for walking us through the inversion for constraints and inversions. That was very helpful. I have a couple of questions already. All right, the first one is a little bit long. Are you ready, Elizabeth and Rob? What happens when the constraints are wrong? For example, the fault is in the wrong place or the depth constraint is not correct as expected. Will the model be forced to fit within the constraints, or will it be allowed to vary beyond them if the inversion sees the need to do so because of the data? This result would then suggest constraints were wrong. It really depends on how firm or accurate your constraints are.
Okay, let me start with addressing that, and I would say yes, this is absolutely a very good question. The degree in which you can trust your constraints is really critical to this process. If you implement incorrect constraints, yes, the inversion will try to honor those, and in this particular case, in the bounds constraint, what you would see if the constraints are inconsistent in general is an inability to reach a fit to the data. So the inversion runs, it's an iterative process. It starts off by trying to add structure to the model until it's able to get a satisfactory fit to the data. If your constraints are wrong, one possible outcome is that your fit can't be achieved. So if I'd push this sediment surface too far down, or I had my southwest trending fault too far through the ore body, it's quite likely I would not have been able to fit the data. So that's one possible outcome. The second possible outcome is that yes, the model can fit the data, but it will honor your faulty constraints, but you might see that the physical property values were large or varied wildly, or didn't look very geologically reasonable. So that's another possible outcome. And I guess a third outcome is that your constraints are approximately right, but not exact. Well, then I think you'd probably find the model will obey those approximately right constraints, and I don't know that there's really too much we can do about it. One thing I would add to that of this discussion is that it is easy to move the constraints up and down. You saw how simple it was for me to construct the upper bound constraint. If I wanted to try different sediment depths, it would be easy, as I'm sure you all know in the channel math, to simply add say 25 meters to the, or 50 meters, or subtract it from these constraint and move the constraints around in the model. So one possible way to explore this space is to create a series of these constraint surfaces and move them around, and then you get some idea of what might be a reasonable set of constraints if you don't have firm information about them. So that's I think some guide to this process.
Great, thank you, Rob. I've got another question from the same person, and it may be part two, so I'm just going to read it, and we'll see how it goes. The fault is only defined to a specific depth, and the mesh goes well beyond. How does the mesh populate all the way to the bottom of the mesh using the GDB math?
Yes, again, an excellent question and a very astute observation. Yes, the mesh, that the fault is depth limited. I have shown it depth limited there because it makes for a better presentation if you don't see the full depth of the mesh. But in the process, when I'm constructing that upper bound constraint voxel, I use the expand mesh tool or menu item in Oasis Montage, and I expand the mesh. I simply expand the mesh sufficiently that it actually defines the entire, or covers the entire volume of the model. So yes, that is a good question, and the answer is that I expand the mesh to fill the entire space before performing the channel math.
Okay, thank you. So our third question, what is the procedure for defining a steeply dipping plane, parentheses, fault or stratigraphic horizon in a voxel?
What is the procedure? Well, this would be similar to this the southwest trending fault that I've used here. This gets into a rather complicated use of, if you like, of the voxel utilities in VOXI. We intend to, or we will, provide further information on how to actually do that, but I will just at this stage say that it's exactly the same process that I showed for the horizontal space of sediments, but in that case for the steeply dipping fault, rotated the coordinate system to make it possible to do this. The question, I'm not sure whether I've answered the question correctly, or the question might be actually how do you display or show these surfaces. This is a GoCAD surface that I'm displaying in here.
Okay, we have another question. Voxel math is a mystery to me. Do you plan to have a future webinar on this topic?
Can I take that one?
Sure can.
We know that just constructing all these constraints, these voxels, is not necessarily that obvious in the beginning. And we have been talking internally to Geosoft to provide such information. There is, if you go to where we have the information online available, there is an example again with Reed Mahaffey where we build a constraint on a dike that goes through the data set. So we intend to use those type of examples and expand on them. The more you ask for it, the faster I guess we'll get to providing you with the details. It may sound complicated, but once you do one or two of them, you will see that it's not that difficult. So again, the way you can produce these is if you can define them in math, define a plane in math, you can always put that math into voxel math or channel math. A few examples will help you produce, go ahead and do these exercises yourself.
Aha, sorry, I've got another question. Would it be possible to generate a wizard to cover some common geological situations?
Well, let me answer that one. I think this is certainly the way that we're trying to go with VOXI. Geosoft is all about providing what we call a natural data experience, a process which is easy for the explorer, so you can get on and explore rather than worrying about the intricacies of channel math. So yes, I believe that. Although I'm not in a position to commit to when this would be done, but we will try and produce some tools which make these things easy. For example, this base of sediments or depth to target, as Elizabeth and I have presented here, is a very common scenario, so a wizard to make that happen would make a lot of sense.
One of the documents, I'm not sure if it's already online, with all the other information and the documents and videos that we're providing online. One of the documents is how to build a model that goes about building a fault, few sedimentary layers with a basement rock and some intrusions in there. And that document describes exactly how you go through and you add the math to produce each layer. If it isn't online, please watch for it for the next few days. It's called Build a Model. Yeah, you can
I'm just
go
going
to Learning Center.
Yes.
And please scroll.
Which document are we looking for, Elizabeth?
It is not there yet. I'm looking down on the left side. It's called Build a Model, and I don't see it up yet.
Okay.
But I know that it's coming online very shortly. So that will give you an insight into how to use math. It's only one model that's built. We will put more as time goes and provide you more
Excellent.
exercises of this.
Excellent. Let me just make sure we don't have any more questions before we end today's session. That is all. No more questions for today. I'm going to pass it back to Troy Wilson to wrap us up. Thank you.
For the great feedback. As you know, this is the pre-release program, and again, part of the program and part of the success of the program is you as geophysicists helping us understand what we need to do to create, as we talk about this great natural experience for VOXI and VOXI users. As part of that program, we're going to add some more tokens to your account. I think there's some people talking about the nice thing about it is that it's almost a reward system, but you guys are important to us and appreciating what your feedback is on how to use our VOXI inversion service. Again, we haven't heard feedback from everybody, but feedback is very important to us. Things that you're finding are barriers to getting your job done, things around our new Geosoft ID, our VOXI Earth modeling, our information products and service, what things you'd like to see to help you take you through the inversions. How you use customer help in our forums, and anything about the new approach of how we're even purchasing, or what a token means, or how that might impact your business is very important to us. So thanks again, everyone, for participating in the seminars. We're doing our utmost to get information out there as a successful launch in next quarter of 2012.